Long day. Okay, so we are back online. You missed some parts on the noise and how it helps regularizing, and the little updates to the mean and the covariance function, which you should be able to derive this for yourself. And then we had a few little quizzes about how it helps regularizing, how there could be an interaction with the length scale parameter, and so on. Okay, so here I provide us an intuition to the noise parameter, which is absolutely useless because we don't have the large projection and you will never be able to see what I'm actually trying to show you. But if you had eagle eyes, you would be able to see that on the left side we have a noise-free data set, right? So we fit every sample sort of training point perfectly because we have no uncertainty about our data, so the data is assumed to be perfect, okay? On the right side, we don't assume the data is perfect anymore, so we impose some variance. So now, in principle, you don't have to, and this is really hard to spot here because this is not the point scikit-learn produced this figure wanted to make. I think they wanted to make the point that the uncertainty intervals have grown, right? Because you have intrinsic noise, so your prediction intervals, your uncertainty estimate has intrinsically increased even at points which you have observed. But in principle, concerning your mean function estimate, you saw that earlier on, you also don't have to go precisely through that point. You will see another example of this later on. That's often true, right? Because we know if there's noise on the function, uncertainty on the function, then maybe our best estimate in terms of generalizable predictive skill would be not necessarily hitting every point spot on, because that could be indicating overfitting, right? Okay, so how do we do that? Hyperparameter learning and model selection. So like in any machine learning method, we have, you saw that in the RBF kernel earlier on, we had this length scale parameter, for example. We have this sigma parameter for the noise that we now added on. So there are parameters that we can learn and potentially cross-validate. And that means we have to do model selection. So how do we do this? So I wrote this somewhat more verbose so you can work through this on your own at home, which is good because now you will have to. So if we have our multivariate joint distribution of training and testing, and we have the form generally mean functions covariance kernel, which we can specify in some way. Again, you have seen one example, but I will give you more examples later. But let's just assume these kernels can be quite diverse in terms of their setup. Then typically as I already mentioned, for the mean function, we can assume something that is constant or even zero if you normalize to the training data average. The kernels, as I said, are subject to certain hyperparameters, and these are often dropped in the notation that you see in introductory chapters on Gaussian process regression, which is confusing for people who are not used to non-parametric methods, because they think it's non-parametric and then it can't have parameters. So that's actually an issue. So I will introduce it in the notation on the next few slides sporadically, where I want to highlight that this is dependent on hyperparameters that we can tune. And these are typically optimized subject to something called the log marginal likelihood, which is the probabilistic expression of something similar to least squares error, if you want to put it very broadly, maybe with some regularization if you have noise. But you will see an expression for this on the next few slides, and I will link to all of this. And because in this case, the likelihood you try to maximize, you still have to take the derivative, which means that gradient descent methods will be important. So what is happening in the background is sort of what you've seen before. LBFGS is quite popular, and it's something you can set almost as an additional hyperparameter if you wanted to look at it from a neural network perspective. And now, very important, the log marginal likelihood is not always convex, typically not at all, right? So again, you can get stuck in local optima, and what you typically do is you have to initialize the hyperparameters somehow. So you start somewhere on this hypersurface, right? And different initializations and rerunning the same optimization give you maybe an estimate of if you are stuck on something non-optimal for different initializations. So usually this optimization is not just run for one initial hyperparameter setting. You change the starting point. Now the log maximum likelihood or log marginal, however I express this now. log marginal likelihood, I wanted to say. This is a typo I have to correct. Log marginal likelihood, you can express in a probabilistic fashion with the likelihood and the prior that you update to get the posterior. And then you can express the prior logarithmically for Gaussian distributions as such, where you have just this offset which you can't optimize, but then you have two terms which are dependent on your kernels, and as kernels they are dependent on your hyperparameters. And ultimately you can then derive an entire expression for your marginal likelihood, which looks like this, again with this sort of regularization term here, and the kernels depending on the hyperparameters, right, and this constant offset, which doesn't really matter so much for your optimization. Okay, so this is the expression where you typically try to optimize and then take a derivative of. And what we have to do for this as well is to take the inverse, right? So this is where the inverse becomes important and expensive. Yeah, Cholesky decomposition is something you could try. So there's an algorithm described in Rasmussen and Williams that you can run through if you're interested. But the complexity you can't change, right? It's O and 3 for the samples. So if you have a lot of samples, that's going to be slightly sort of the limiting step here, limiting mean. Okay, so what are these hyperparameters for the RBF, radial basis function, or also referred to as squared exponential kernel? We have already talked about this. So we had this length scale, and we had potentially some noise we could add, and we also, I didn't discuss this too much, have this pre-exponential factor, which is just a scaling factor. In reality, you don't, it's rarely talked about in actual implementations, but let's just keep it in here for some time, because this is a figure from the Bible, in this case, where we preset, so not optimize the length scale for an RBF kernel, and we have data points indicated by the crosses here, okay, and subject to different length scales, we fit the RBF kernel, and we optimize according to the log marginal likelihood. We optimize the noise around those estimates, okay? So these are free, the noise are free parameters that are optimized. So for L equals 1, length scale equals 1, you get this fairly smooth function going through all the points. For length scale, a shorter length scale, you can see how the function becomes much more nervous, right? And now actually in comparison, you can see that they go precisely through the points, so it's much more flexible to adjust to the training data, whereas here some of the data wasn't actually on the direct path of that function. And then if you increased instead the length scale, you get a longer range of variation, right? So now you don't fit these points at all precisely anymore. What instead happens is that if you look at the noise terms here, that in this case you fit the training data points perfectly, and it seems to assume from the log marginal likelihood that on these specific points the noise is basically 0, whereas here the interpretation is completely different given the different length scale. So suddenly, because you can't fit every point perfectly because your length scale is too large, basically it has to be compensated by interpreting it as noise on the data, if that makes sense. So these things are interacting, right? So again, hyperparameters are not independent. And clearly, depending on what process you assume to be underneath, do you think that a slower variation, right, a larger scale variation like this is realistic for your data, or this, you might come to different answers. So in terms of a log marginal likelihood, the top figure here was actually selected by quite some margin, but I could imagine many situations in applied disciplines where you rather want to have this here. And just to give you one example of this kind, so I use this for, in industry, looking into sensor calibration. To summarize it very bluntly, measurements are expensive, so if you have a high performance measurement device for multiple species of atmospheric composition, you easily pay on the scale of a few tens to hundred thousands of US dollars. So that's going to be expensive, whereas what we sometimes are looking for is very high density measurements pretty much in every street. You can even have exposure different on different sides of the roads and so on. So you would like to look for high density, high-frequency measurements, and that's only possible if you have low-cost sensors, which sometimes cost on the order of $10 US for certain species. So much, much cheaper. The problem with these sensors is they still have to be calibrated, and they're somewhat unreliable because they're cheaper. So, and what we basically tried to do is, could you do the calibration by co-locating this? This is quite a common approach by now, with high-performance measurement stations and calibrate it against the signal that the high-performance measurement station has measured. So you do sort of passive calibration, and that can be done with machine learning. And typically what you find is, yeah, for a given location you can do this fairly well, and again, eagle eyes are necessary. Here are 4 different approaches. One is multiple linear regression, another one is rich regression, which is linear but regularized. Then we have the Gaussian process regression in blue, and random forest regression in red. And what you can't see is, for a variety of metrics, you get very similar performance on the same location. But one question we, for example, asked ourselves is extrapolation, and this is where the length scale comes into play. So if you took this sensor calibration and took it to, so this sensor that you calibrated at a specific place, right, and took it to a different location, would it still reliably measure what you see? And this is shown here. So once you take the sensor across to a different location, this will be the reference high-quality measurement. This will be your low-cost measurement. And you can generally see in gray this multiple linear regression that this is performing not so well once you take it across. So machine learning does help for most of the domain. But random forest regression in red is sort of leveling off at values, so this is in micrograms per cubic meter, that it hasn't seen at training, right? So this new station is far more polluted than the previous station. So it's just, when it reaches that threshold, it just says always the same value. Okay, so that's the problem with extrapolation. And you can see that linear, regularized, rich in this case, performs better for a much extended interval. So maybe you can add another 50% or so of pollution before also rich regression gives up and says, okay, this is becoming a non-linear process. I can't predict this anymore. And then you see in between blue, the Gaussian process regression. So Gaussian process regression, despite being a non-linear method, especially we used a more complex kernel design here, goes somewhat beyond what random forest can do. And this is because of the length scale. It depends on the length scale that you have learned from the intrinsic data properties here. So we didn't preset this, but because there was a length scale, it could extrapolate to a certain degree, if you see what I mean, before it stopped working. Just to give you an intuition for how these... So now obviously if you wanted to extrapolate, we could have played with setting a certain length scale or so, but then probably we would just have transformed it into a linear method. Okay, this is just a summary. Key advantages is it's quite a versatile method to interpolate and therefore to predict between observations. You have empirical confidence intervals which should be enjoyed with care, because it depends on your choice of prior and how you define your noise and so on. So it's not completely objective, as it sometimes be interpreted. But yeah, overall the kernel designs that I will talk about next make it highly flexible. The main disadvantages are it's expensive because of this matrix inversion and because you have to keep track of all the samples potentially. But again, as you can imagine, people have thought about this, and approximation methods, faster approximation methods do exist, and are discussed also in the book here, chapter 8 by Rasmussen and Williams. And I also implemented a very basic version of a sparse Gaussian process in assignment 9 that you could take and improve if you wanted to. And then the curse of dimensionality can hit you as long as you don't use the noise parameter to regularize to a certain degree. Okay, kernel design. Let me try to do this in 5 minutes, because I don't think it's super intuitive, given that you have understood everything I've said so far. So you have your prior, right, usually assumed to be 0. You have your covariance function, which will depend on certain parameters that you optimize subject to the log marginal likelihood. And the typical workflow is now you run the optimizer several times with initial parameter values set for the kernel, and then choose from a range of values that you initialize for that kernel to see if over that space you can find a better solution in terms of optimization. And now these, I should warn you that as you do this, really do multiple initialization runs, try different ranges for your hyperparameters if your function is not performing well. Gaussian processes are so versatile that at least for an interpolation project, they should work decently well. So if something is not working at all, you're probably in the wrong range of parameters you search over. I think this I can jump. There's a difference between different types of kernels. So if they only depend on the distance between input points, or also about the absolute value of those points. So this is the difference between stationary kernels that are invariant to translations in the input space as a result, or non-stationary kernels. And here's just one example for such a initialization using scikit-learn. So this is the most basic way how you can get about Gaussian process regression, where you have an RBF kernel, so radial basis function kernel, plus a white kernel, so you can combine kernels as well. I will touch on this very briefly below. And then you have basically bounds that you specify. So once you restart your optimizer, you will randomly select from these intervals that you think might be realistic. And these might also include not just length scales, but periodicity parameters. So some of the kernels can have periodicities, and that's clearly important if you have data where you assume that there might be a diurnal cycle or a seasonal cycle, which we typically have in the climate and environmental science. Okay, and then it's all about log marginal likelihood. So the RBF kernel you have already seen, and the intuition, and you can create different priors, right, from, let's say, or you can create a set of, the Gaussian process is the set of functions that is defined by this kernel. You could think of different kernels, different length scales. We've already seen that. So this was pretty much just to give you completion. This is by Sophie Wilkinson, a former PhD, doctoral researcher in my group, who gave this nice introduction. You could have the same prior, right, and then you constrain it with different data. Let's say on a linear data set, this particular prior might do not so well in terms of doing between the points, whereas maybe for a periodic data set, the same prior does much better. So the choice of prior matters depending on which type of data properties you expect. And the length scale can be scalar, or it can vary with dimensions. So you could have isotropic or non-anisotropic definitions. And this will define how your Gaussian process looks like in high dimensions. Other kernels are the rational quadratic kernel. So this just allows you to include multiple length scales, if you like, right? So it makes your prior somewhat noisier than the distribution of length scales than you had for the RBF kernel. And maybe this is just for you to know, if you use the RBF kernel, which is sort of the off-the-shelf standard kernel that you would use for Gaussian process regression, this can particularly lead to problems. It has a few very nice properties for continuity, but if you have a very discontinuous data set or very short length scales in your data set, then this will determine your overall length scale. So if you have very sudden fluctuations, you might be in trouble because the smallest wiggle, so to speak, in your function determines that. And I wrote a few hints and tips. So if this happens to you, there are some obvious signs for how you can spot that the RBF is not a good kernel to choose here. The periodic kernel is what I just mentioned earlier on. So here you have an additional hyperparameter called P. So it's when you talk about periodic stuff, you usually have a sine or a cosine function included, right? And you just get a different prior distribution, which will also then, as a result, determine what you could get out on the posterior, clearly. And if you want to get a more extensive introduction to this, so there's a nice website by Duvenot called the Kernel Cookbook. He already wrote this a few years ago, giving some of these intuitions that I here provide. But the key point is you can also combine kernels, right? So RBF times periodic would be the locally periodic kernel, or you could have a linear kernel. So the linear kernel on its own would be a bit boring because it would just do Bayesian linear regression, which I talked about at the beginning. But in combination with other kernels, it can sometimes give you better performance. Because if you multiply a linear kernel times let's say a periodic kernel, you could model trends, for example, as well. But again, I leave this up for you to review. I don't have to hold you here. I think it's much more efficient if you sit over your kernel design, go through these slides and think about, okay, what is my problem? Which kernel would be useful? And maybe in a few years go back to this and think about more. The Martin kernel is very popular, so this depends on the Bessel function. Basic intuition here is that you have this additional parameter nu, depending on your Bessel function, and this defines a much more noisy process than, let's say, for example, the RBF. And again, you can have here a length scale that is depending on the dimensions. So if you have many input dimensions instead of just two, like I show here, right? So usually you have high dimensional problems. It can be useful to vary the length scale in high dimensions. What you can actually also do is have active dimensions in more complex. So scikit-learn doesn't offer this as far as I know, but if you work with something like GPy or GPFlow in particular, I've seen it, done it a few times, you can switch on certain active dimensions for certain kernels. So if you think that certain dimensions behave differently to other dimensions, you can specify specific kernels for specific dimensions, if you see what I mean. Okay, very important, because you have work with Gaussians, you can combine kernels. So multiplying kernels is intuitively the AND operation, because sort of following the AND operation, because if the kernel has a high value and the kernel you multiply it by is also a high value, then you get sort of a positive acceleration, whereas if one of the kernels has a low value and you multiply them, they would switch each other off. And for the OR operation, it would be sort of the sum of the kernels intuitively. But you can come up with all sort of mixtures, and I linked here as well to a paper by Roberts looking at time series, just showing you that, let's say, the rational quadratic kernel here, if you multiplied this by some sort of periodic kernel and added some white noise, you would get very different priors, right, out of this, just by combining different kernels. And it really depends on what you expect your data set to look like, right, and what processes to be represented. In this way, you can target your data quite specifically. Again, this is a slide for you to read, but I think it's intuitive to say that every time you have all these different kernel choices, there's an element of empirical work involved in here, so you can maybe inform yourself with your prior knowledge about the problem, but usually you have to try at least a few different combinations, a few different hyperparameter ranges you search over, which is the initial settings basically, to get your optimal approach, and maybe also combinations of kernels, because it's not always intuitive. Let's be so frank. And again, people have written ways to combine certain commonly used kernels and do that for you, similar to a neural architecture search, so to speak. Here you're sort of a kernel search over certain standard kernels, what might fit best for your problem. So if you want to go into really much detail about this would be a way to go. And the way to do that, as I said, so if you just want to do something quick and off the shelf and intuitive, you can use scikit-learn. But there's a lot of software out there, especially for GPU computing by now as well. So I linked here Model Zoo for GPs. It's a nice overview website, but good starting point could be GPy or GPyTorch, GPFlow. They have different flavors. Yeah, and maybe assignment 9 would be something to try this, even though it has a very large sample size. So I give some recommendations how to maybe still use Gaussian processes in the assignment, despite having this very large sample size, which makes it somewhat more difficult to use. This is not interesting for you, so I'll cut this very short. It's not interesting for you because mostly it's referring back to my own history. So Gaussian processes have been used, Gaussian process emulation in particular, Gaussian process regression has been used in climate science for quite a while. Maybe it actually outpaced in that sense, because it was a method that's around for a long time and it has this intrinsic uncertainty intervals. It outpaced machine learning on this, so the raw machine learning idea. So at that time they really talked about just pure Gaussian process emulation. I can remember Lindsay Lee from Leeds giving a talk about this in our department years ago, when I was still in the UK. And she talked, for example, learning from observational data and from model data, how cloud condensation nuclei, so CCN, form, which is important for how aerosols affect clouds and therefore the global energy budget, and how you could then decompose this into uncertainties and parameters, and how you could try and understand which parameters you would have to observe better to be able to constrain the uncertainties on these processes. So yeah, it has been around for a while. Okay, so I ran through this fairly quickly given the time. I apologize again for the technical issues, and that it's pretty much too many slides for too little time, but this is partly because I wanted you to have material to refer back to. So next week will be about transformers, and hopefully I can keep this somewhat more compact, and I will talk about the coupled model intercomparison project, because I felt I talked so much about climate models and so much about CMF6 indirectly that it would be nice for you to know, and I definitely think that students in my group will always get to know about CMF6 at some point. So probably something good to at least describe in 10 minutes or so in one of the lectures. Okay, here a quick summary. So yeah, I didn't talk about classification today, but I hope it came across how broadly speaking this kernel idea, the covariance, is important for using it in regression. Key ingredient is here already the kernel or the covariance function. There's an empirical component to how you choose your kernel for sure, and there are multiple software packages you can use from a practical point of view. See assignment 9. And then if you are suffering from overfitting, maybe think about, instead of throwing Gaussian processes away, think about maybe ways to cross-validate your noise term. And again, I provide a scikit-learn implementation for this in assignment 9. Okay, I'm sure there are many questions, but are there any questions that are burning, apart from will the screen work next time? No? Then again, apologies, and see you next week, Thursday and next week for the lecture for transformers. Bye.